Good morning children. In today's class, we are going to learn about factor theorem. First of all, what do you mean by factor? Suppose I consider an expression x square minus 5x plus 6. I try to factorize. I get x minus 2 and x minus 3. Supposing I make it equal to 0 and make it as an equation. Now I give the word roots. Factors, I say x minus 2, x minus 3. But when I say roots, I will say x is equal to 2, x is equal to 3. The same idea, let us expand to the determinant in a matrix A. Every term is a polynomial in X. And if I put x is equal to A in that particular determinant when I evaluate, suppose the determinant vanishes like equal to 0, I will call x minus A is a factor of the determinant. So I will call x minus A is the factor of the determinant A, or I will say x is equal to A is a root of the equation determinant A equal to 0. Let us see an example here. You are given a determinant like this. Say x plus 1, 3, 5, 2, x plus 2, 5, 2, 3, x plus 4. My question is, I need to put x is equal to some suitable value so that the determinant should become 0. When the determinant will become 0, we have an idea any two rows or any two columns are identical. So how shall I make the rows or columns to be identical? Think of a value. See, if I put x is equal to 1. So what I am putting now? X is equal to 1 in the determinant. See what happens? 1 plus 1, 2, 3, 5. Second row, 2, 1 plus 2, 3, 5. Third row, 2, 3, 1 plus 4, 5. See, I get 2, 3, 5. Row 1, row 2 and row 3 are all the same. Or else I will say the 3 rows are identical. Whenever 2 rows are identical in a determinant, I will immediately conclude my answer is 0. So according to factor theorem, I will say x is equal to 1 is a root for this equation, or x minus 1 is a factor of the determinant. So when I say 2 rows are identical, x minus 1 is a factor. But in this problem, 3 rows are identical. So I can say x minus 1 the whole square is a factor. As we do exercise problems, you have to guess in certain problems. But many problems, they give you the answer like this. X minus 1 the whole square into x plus 9. Something like this they may give. So this right hand side will give us a clue. If I see x minus 1, put x is equal to 1 in the determinant and check whether the determinant vanishes. Whether 2 rows identical or 3 rows are identical. If 2 rows are identical, it is a factor once. If 3 rows are identical like this, it is a factor twice. So multiplicity we say when I say root. So if the root comes twice, we say that particular root has multiplicity 2. We are given maximum 3 rows in determinants. So if you want, you can extend it for higher powers. But we are restricted to only third order. So maximum 3 rows or 3 columns may be identical in our problems. So declare the whole square is a factor. Now, there are some more ideas that we need to remember. While doing problems, how are we to proceed when I say factor theorem? You are given a problem like this. First step, look at the RHS. The brackets, the factors, whatever they give in RHS, you make equal to 0. And suitable values, we substitute accordingly. That is my first step. Once I find out the factors, I have to check there are extra factors. How to find the extra factors? Look at this example. RHS will be A minus B, B minus C, C minus A. As I put A equals B, I will get R1, R2 identical. In the same pattern, I can check B minus C, C minus A are identical. This type of problem, I can use the word cyclic and symmetric. What do you mean by the word cyclic? Wherever A comes in first row, it becomes B in the second row. It becomes C in the third row. So cyclically, A, B, C are changed. Such problems we call cyclic and symmetric. In cyclic and symmetric problems, if I show one particular factor, I can immediately conclude the remaining two are also the factors of the determinant. Now, I must check something called degree. How to find it? When I see here, 1 is a constant. Constants have the degree 0. Ignore. Diagonally, I see the elements. I have 1 B C square. For 1, the degree is 0. For B, the degree is 1. For C square, the degree is 2. Adding it all, degree of the determinant is 3. Look at the RHS. What is degree of A minus B? A minus B, when I take A degree 1, B degree 1. Can I say degree to be 2? No. When we subtract or add, look out for the higher degree. So degree of this particular factor is 1. Degree of this particular factor 1 and this particular factor 1. So what is the total degree? 1 plus 1 plus 1, that is 3. LHS degree 3, RHS also degree 3, and then extra factor I have to assume as K. How to find K? Let us see exercise problems in detail for that. And do not stop your answer with K. Once you find K, put it back in this step. Now look out this problem. Here, my answer will be A minus B, B minus C, C minus A into A plus B plus C. The same pattern, I will show 3 factors. A minus B, B minus C, C minus A, I can show. But what is the degree of the determinant? 1, no degree. B degree 1, C power 3. Altogether, the degree is 4. But RHS, we proved only A minus B, B minus C, C minus A. What is the degree? Together, it is 3. Whenever the difference of the degree is 1, I will assume extra factor as K into A plus B plus C. Suppose LHS degree 6, RHS degree is only 4. Now the difference in degree is 2. Whenever you have the difference in degree 2, I have 2 degree combination A square plus B square plus C square. Also some other constant into AB plus BC plus CA. Remember, when I find out the degree of determinant and factor, if the degrees are same, extra factor is only K. If the degree is missing, that is 1 degree is the difference, extra factor is K into A plus B plus C. If the degree is 2 in difference, LHS may be degree 4, RHS may be degree 2. LHS may be degree 5, RHS what we have proved as factors, the degree may be 3. So in such cases, assume the extra factor to be like this. Let us proceed into exercise problems and understand better. Exercise 7.3, question number 4. Show that. Look at the determinant given. Here I have B plus C, C plus A plus B. A, B, C. A square, B square, C square. Such problems we call cyclic symmetric problems because wherever A comes, the next step B, the next step C. It is cyclically changed. Such problems we call cyclic symmetric problems. And such problems we can use factor theorem whenever RHS is a product of some factors. Each one I call factor. The given determinant, let us call in the name A. So determinant A is B plus C, A squared, C plus A, B squared, A plus B, C squared. Now, to show this factor A minus B, put A minus B 0, I get A equals B. So, wherever A comes, we will put B in the determinant. As I substitute, determinant becomes B plus C, C plus. Wherever A comes, I am going to put B. A plus B. A is B. So, B plus B. The second column, it is B, B, C. The third column, B square, C square. When I substitute, I can identify this first row and second row are identical. Whenever two rows are identical, we know the determinant itself becomes 0. And when the determinant is 0, I declare A minus B is a factor of the determinant. Here we named determinant A using factor theorem. Remember the idea? We are using factor theorem to check whether two rows or two columns are identical by putting the first factor to be 0. The same pattern we will go on to B minus C. Put B equals C in the determinant. Determinant A becomes, wherever B comes, I must put C now. So, it is C plus C, C plus A plus C. Second column, A as it is, B becomes C, C as it is. A square, B square becomes C square and then C square. Again, I can check R2 and R3 are identical. So, this is also 0. Therefore, I can declare B minus C is a factor of determinant A using factor theorem. As I have proved A minus B and B minus C, I can very well use similarly C minus A is also a factor of the determinant A. Once I have proved three things, find out degree of determinant. This is one method. Or you can also check whether this bracket becomes 0. So if I put A plus B plus C equal to 0, wherever A plus B comes, I will put minus C. Wherever B plus C comes, I will put minus A. Wherever C plus A comes, I will put minus B. So this is what we are going to put in the determinant. So what happens? Determinant A equals B plus C minus A, C plus A minus B, A plus B minus C. The second column A, B, C and the third column A square, B square, C square. In the first column, minus symbol common. If I take it out, I get column 1 and column 2 are identical. Therefore, the determinant vanishes. So, I can also say A plus B plus C is also a factor of determinant A. As I have completed showing the 4 different factors, let me find out the degree of the determinant. To find the degree of determinant, count the degrees of the diagonal terms. Here B plus C. See, B plus C. What is the degree? B degree 1, C degree 1. Together, the term has the degree 1 only. Degree, when I say, I mean the highest degree. Suppose I have BC. Now what is the degree? It is multiplication. I have to add the degrees. So the degree is 2. Now diagonally, what are the terms? I have b plus c, I have b, I have c square. This is multiplication. Here the degree is 1, here the degree is 1, here the degree is 2. Multiplication tells me add the powers, so I get 4. So what is the degree of determinant A? That is 4. What is the degree of the factors? C minus A, degree 1. B minus C, addition or subtraction, you write only the highest degree. So 1, 1, 1, here also 1. How many degrees altogether? As we multiply the 4 factors, 1 plus 1 plus 1 plus 1. The degree is 4. Whenever you have degree of the determinant and degree of the factors same, the extra factor we just introduce a constant. To find k, what is the procedure? Write the given determinant, that is b plus c, a square, c plus a, b square, a plus b, c square. This is the given determinant. K, the extra factor, into all that we proved already. A plus B plus C into A minus B into B minus C into C minus A. To find K, there are 2 methods. Method 1. Compare the degrees of terms in both the sides. But A, B, C are repeated all over. Comparing the degree will be a difficult task. What is the second method? Put convenient values for A, B, C so that no side can vanish. Let me put A is 0, B is 1 and C is 2. As I substitute in both the sides, what is A, B, C? Check what you get. Determinant B plus C, I get 1 plus 2. A square, 0, 0 square. C plus A, 2 plus 0. B square, 1, 1 square. A plus B, 0 plus 1. C square, 2 square is 4. This is equal to K into A plus B plus C. I get 0 plus 1 plus 2 into A minus B, 0 minus 1, B minus C, 1 minus 2, C minus A, 2 minus 0. As we simplify, it is 3, 0, 0, 2, 1, 1, 1, 2, 4 equals to K into 1 plus 2, 3, 0 minus 1, 1 minus 2, minus 1, 2 minus 0, 2. Let us expand along first row. What are the symbols in first row? Plus, minus, plus. As I expand, it is 3 into. Hide the row, hide the column. I get 1, 1, 2, 4. 0 into anything 0, 0 into anything 0, forget it. Right hand side, I have minus into minus plus. 3 into 1 into 1 into 2, that is 6 into K. As we simplify, it is 3 into 4 minus 2 equals to 6K. 4 minus 2, 2 into 3. 6 is equal to 6K implies K value is 1. Once I know K value, put K value back in the given equation, that is 1. Put K equal to 1 in equation 1, we get B plus C, A square, C plus A, B square, A plus B, C square. The determinant equals to K value 1, so I can write 1 into, which I can ignore. I have A plus B plus C into A minus B into B minus C into C minus A, and that is the answer. Exercise 7.3, question number 1, show that the determinant RHS, we have factors. So whenever you have factors type, I can use factor theorem. Take the given determinant as determinant A. If I want to show x minus A as a factor, put x minus A 0, I get x is equal to A. So wherever x comes, put A in the determinant. Wherever x is coming, I am putting A. So it becomes A, A. As I look out, 3 rows are identical. Whenever 2 rows are identical, x minus A is a factor. If 3 rows are identical, we say x minus A the whole square is a factor. 2 rows, x minus A power 1. 3 rows, x minus A the whole square is a factor of determinant. Now, wherever x is coming, we put minus 2a because the next factor is x plus 2a. If I put x plus 2a 0, I get x is equal to minus 2a. So in the given determinant, wherever x comes, let us put minus 2a. The remaining terms copy as it is. As I check, any columns identical? No. Any rows identical? No. So we will try to make any 2 rows identical. Let us add R1 and R2. New R1 is R1 plus R2. Minus 2a plus a minus 2a, a plus a. Keep second row and third row as it is. As I check, in the first row, let me take minus sign out. It is a minus 2a. Second row, a minus 2a. Third row, a minus 2a. Now, R1 and R3 are same, or I will say identical. When R1 and R3 are identical, we can declare x plus 2a is a factor of determinant. Why? Because whenever rows are identical, I get determinant value to be 0. When I put x is minus 2a, if the determinant becomes 0, I can immediately conclude x plus 2a is a factor of the determinant. What is the next step? Find out the degree of the determinant. The degree diagonally you can multiply x into x into x power 3, or you can add the powers while multiplying. No power tells me 1, 1, 1. As I add the powers, the degree of the determinant is 3. How many factors have I proved? X minus a the whole square and x plus 2a. So for this, what is the degree? X square. So degree is 2. X power 1. So degree together we add. So the degree is 3. Whenever both the degrees are same, degree of the given determinant and degree of the factors are same, then extra factor will be only a constant. How to find that constant? You can compare terms in both the sides, or you can put convenient values for x, and hence let us find out the value of k. The given determinant we compare with the factors. Extra factor k and already proved factors x minus a the whole square into x plus 2a. Let us compare coefficient of x cube on both the sides. How do I get coefficient of x cube? Here I have x into x into x. I have the coefficient of x cube is 1 in the LHS. In RHS, k into, this is x square, this is x power 1. So together x square into x power 1, x cube I get into k. So 1 equals to k, and therefore we have proved xAA AX. The determinant answer is K value 1. So I can just write X minus A the whole square into X plus 2A is proved. Question number 2. Show that B plus C, A minus C, A minus B, B minus C, C plus A, B minus A, C minus B, C minus A plus B equals 8ABC. Again RHS are factors. A, I can write A minus 0. B, I can write B minus 0. C, I can write C minus 0. So wherever A comes, let us put 0 in the determinant, which is named as determinant A. B and C copy as it is. A is 0, so it is minus C, C, C. Here A is 0, so I get minus B, B, B. In second column C is common, in third column B is common. If I remove, I get B plus C, B minus C, C minus B as first column. In second column, I am taking C as common. It becomes minus 1, 1, 1. Third column, minus 1, 1, 1. As we check, column 2 identical to column 3. Therefore, determinant A becomes 0. Whenever determinant A vanishes, I can say A minus 0. That is, A is a factor of determinant A. Let us put wherever B comes 0 in the determinant. So, B value 0, B value 0, B value 0. In the second column, I write as it is. Third column, wherever B comes, let us put 0. A minus A and A again. Now, as before, C is common in first column, A is common in third column. I am left with 1 minus 1, 1. Second column, write as it is. Third column, again 1 minus 1, 1. I can check column 1 identical to column 3, and so my answer is 0. 0 into any number, 0. Therefore, I can declare B minus 0 or B is a factor of determinant A. Similarly, I can prove C is also a factor of A. What is degree of the determinant? Every term here has the power 1. So, degree 1, 1, 1. Diagonally 1 plus 1 plus 1. When I multiply, I add the degrees. So, degree of the determinant is 1 plus 1 plus 1, that is 3. Now, I go with the factors. I have proved A, B, C are the factors. Again, the degree is 1, 1, 1. Add the powers. I get degree to be 3. When both the degrees are same, extra factor will be just K. Now, the given determinant, I write K into whatever factors I already proved. K into ABC. Extra factor and already proved factors. Call this as number 1. I will put some values for A, B, C. This is second method to find out the value of K, so that no side can vanish. So, I cannot put A or B or C to be 0. If I put any of the values 0, 0 into anything will give me 0. That will not help me to find K. So, put values for A, B and C in such a way that A into B into C should not become 0. Let me put A is 1, B is minus 1 and C is 2. As I substitute, 1 becomes, wherever B comes, minus 1. Wherever C comes, plus 2. So, we substitute 1 minus 2. 1 minus of minus 1 is plus 1. B minus C, minus 1 minus 2. C plus A, 2 plus 1. B minus A, minus 1, minus 1. C minus B, 2 minus of minus 1 plus 1. C minus A, 2 minus 1. A plus B, 1 minus 1. As we simplify, it is 1 minus 1, 2. Here I have minus 3, 3 minus 2. Here I have 3, 1, 0. This is equal to K into ABC. K value I don't know. A value 1, B value minus 1, C value 2. Or if I simplify, what is K value? 1 into hide the row, hide the column. I get 0 plus 2. Minus of minus 1 becomes plus 1 into hide the row, hide the column. 0 plus 6 plus 2 into hide the row, hide the column. Minus 3, minus 9. You should know to directly expand without writing the steps by now. 2 into minus 1 into 1 into k, it is minus 2k. Or we get 2 into 1, 2. 6 into 1, 6. Minus 12 into 2, minus 24, that is minus 2k. I get minus 16 equal to minus 2k, or k value is 8. Is my answer over? No. Put this k value back in equation 1. So substituting k equal to 8 in 1, I get the answer. Let me write here. Determinant of b plus c, b minus c, c minus b, a minus c, c plus a, c minus a minus b, b minus a plus b equals k value 8, a into b into c. So, what are the steps in doing factor theorem? The given problem RHS will give me the clue. If the RHS is A, B, C, wherever A comes, I put 0 in the determinant. As I put, I try to achieve 2 columns or any 2 rows to be identical, so determinant becomes 0. Whenever the determinant is 0, I can immediately conclude that A minus 0 is a factor. A minus 0 is nothing but A, so therefore A is a factor of determinant A. The same idea, I use B equal to 0. And I can similarly declare C is also a factor of determinant A. Now the degree, cross diagonally, I check 1, 1, 1. The degree is 3. The factors that I got A into B into C, the degree is 3. Both are equal. Extra factor is K. Now the given determinant 8, I don't know, which I need to find out. So the extra factor K into A into B into C. As I know, I can do K value in 2 methods. I can compare the degrees, or I can put convenient values for A, B, C. You can put any values. These are our own choice. To make our calculation simple, you can put A1, B1, C is minus 1 also. So put the values in both the sides. Check what value you get for K. As we get K value, do not wind up the problem. K value should be substituted back here. So K value 8, which we have written, and this is the answer to be proved. Try 6th problem yourself and verify your answer. Given RHS x minus y, y minus z, z minus x. Put each factor 0. We get x is equal to y. Put it in the determinant. I arrive at C1 identical to C2. Put y equals to z. Again C2 identical to C3. Similarly, I can declare z minus x is also a factor of determinant A. Degree, when I say Diagonally check the degrees. 1 being constant, the degree is 0. Forget it. Y power 1, Z power 2. So together 0 plus 1 plus 2. The degree is 3. Degree of the factors: x minus y 1 degree, y minus z 1 degree, z minus x 1 degree. When I multiply, add the degrees. 1 plus 1 plus 1, it is 3. Whenever both the degrees are equal, let the extra factor be k. To find k, put suitable values for x, y and z so that no side becomes 0. As I simplify, I get k is 1. Put k value back in this equation. I get the required result.